Welcome to this video on conditional probability and tree diagrams. By the end of this video, you should be able to use the general multiplication rule to calculate probabilities. You should be able to use a tree diagram to model a chance process involving a sequence of outcomes and to calculate probabilities. And, when appropriate, use the multiplication rule for independent events to calculate probabilities. Alright, so we played a game where we had 5 cards. There were 2 aces and 3 kings. And so we would shuffle them so we can't see, and then we would deal a card, and if you're a winner you'll get 2 of the same cards. If you don't have 2 of the same cards, you're a loser in that round. So I'm a loser this time. Shuffle them up. And then I deal a second card. I'm a winner this time. So I'm going to go through 10 rounds to give us some data to look at, and I'll be right back. Alright, so after running my 10 rounds of my experimental probability, let's see what I've got. How many times did I win out of the 10? I won 1, 2, 3, 4 out of the 10. Okay, so the probability of me winning was 4 out of 10, which was 40%. Alright, in our class, there were 29 people and each person played the game 10 times. So we had 290 rounds played. Of those 290 rounds, 124 of them were winners. And when you calculate that out, we got 0.423. So about 42.3% wins. Okay, so that's our experimental probability. Let us take a look at the theoretical probability, and we're going to use a tree diagram. So the tree diagram has branches, and it's essentially from the beginning to the first outcome, you'll draw a line, and then from the first outcome to the second outcome, you can draw a line, and we could keep going, and the tree diagram can get much bigger. But the idea is it helps us it gives us a nice sample space, and then we can answer questions based off the sample space. So remember, we had 2 kings and 3 aces. So at the beginning of the game, if the first card is an ace, what's the probability of getting the first card an ace? So I wrote that backwards. It's 3 kings and 2 aces. Sorry about that. So it'd be 2 out of 5 for an ace. Consequently, there's 5 cards total. 2 of them are aces, 3 of them are kings. Those add up to 1. Okay. And then for the second card, so we've drawn the first card, and if we say the first card is definitely an ace, we've already drawn a card, so there's only 4 cards left because we're not replacing them. If the first card is an ace, that means there's only 1 ace remaining. 4 cards. If the first card is an ace, there's still 3 kings that are remaining. Okay. So let's do this one. If the first card is definitely a king, there's 4 cards left. Of those 4 cards, 2 of them are aces. If the first card is a king, there's only 2 kings left also. Alright, so how this is going to work is we're going to have, this is an and scenario. So as you follow a branch as it goes out this direction, you're going to multiply. Okay, these are and the word and in probability means statistics. So we want to know what's the probability the first card is an ace and the second card is an ace. Okay, so they're going to have these ands in here. So we're going to take our probabilities. So we would say 2/5 times 1/4. I'm going to simplify it down to a decimal answer, would be 0.1. So that means there's a 10% chance of getting an ace and an ace. Now, go ahead and pause the video to fill in the rest of these and come back when you're done. All right, let's see how you did. I got 0.3 for an ace and then a king. I got 0.3 for a king and then an ace. And I got 0.3 for a king and a king. Okay, so these are all my probabilities. Now this is, I said at the beginning, this is a probability model. So remember there's two rules to make sure a probability model is valid. All of the probabilities are between 0 and 1. These are all between 0 and 1. And they should, when you add them all together, they should equal 1. And this is 0.3, 0.6, 0.9, 1. So we're a valid probability model. Now let's take a look at what we have here. This probability is the probability of the first card being an ace. The second probability is the probability that the second card is an ace given the second card is an ace given that the first card was an ace. Okay, so this is a conditional probability that's being multiplied here. So this is where tree diagrams are great for conditional probabilities. So when we come across here, we have, this is our general multiplication rule. This is the very idea of it. So when I show you these notations, you should know how to write them, and you should more importantly know how to read them. But you already know how to do the math for doing this. You understand this times this is a probability. So this is the reason I'm showing you, is so you learn how to read them, but you already know how to do the math. So this number, 0.1, was gotten by multiplying the probability of A times the probability of a second ace, given that a first ace has already happened. So our more formal is the probability of A and B happening together equals the probability of A, which is this, times, that's where the word and comes in when we're going to our second one, the probability of B happening given that A has already occurred. Okay, so that's your formal language for what we have done here. Now, we multiply across each of these branches to get our probabilities. But if I start talking about what do these mean, so this 10% means I got an ace and an ace, and then I'm a winner. 3/10 in this case means I got an ace and then a king. That meant I was a loser that time. Then I have a king and then an ace. That is also a loser. And then king and king. So this one's a winner. So when you look at this, you can see there are two opportunities to be a winner. I could win this way with an ace and an ace, or I can win this way with a king and a king. And that word or from previous videos, remember, is really important. So while you multiply across the branches to get the probability out here, if you're working between the branches with these guys, that's an or situation, and so you would be adding the probabilities together. So let me show you what I mean here. So we want to find the theoretical probability of winning the game. Well, we just said there's two ways to win. We can win by an ace and an ace, or we can win by a king and a king. So the probability of an ace and an ace is 0.1. The word or means add. King and king is 0.3. So the theoretical probability of winning is 0.4 or 40%. Okay, so in our experimental probability, we just happen to get 40%. That happens. Remember, any short run probability is unpredictable. We can't say what's going to happen for sure. Then we had a whole lot more of repetitions. So we got 42.3%, and that is still an experimental probability. We did a bunch of repetitions, but it's still experimental, so it's not going to be exact. But it's pretty close to our 40% that we got here. All right, so now one more thing that we want to talk about is what is the probability that the first card was a king given that the person won. Okay, so let's write that. We want the probability that the first card is a king given that they're a winner. So remember, your condition is what you divide by. All right, so when we set up our fraction, we said, what's the probability of winning? Well, it's 0.4. We already found that number. Of these 0.4 people, what's the probability of getting a king first? Well, this one does not have a king first, but this option does, 0.3. So it'd be 0.3 divided by 0.4, which is 0.75. So there is a 75% probability of winning if your first card is a king. And we could turn this around. We could ask a lot of different questions. Once you have your sample space completed, you can figure out all the probabilities of whatever scenario is given for you. All right, let's flip this over and summarize our learning targets. All right, the general multiplication rule is the first thing I want to talk about. We have talked about the general addition rule. That's the OR situation, and we talked about it for mutually exclusive and not mutually exclusive events. And so for our general multiplication rule, we have conditional events and independent events. So we have conditionals are going to be dependent because your probability depends on what happened before it, and we have independent situations. So for our dependent situations, to find the probability of A and B, you'll take the probability of A and multiply it to the probability of B given A has already occurred. So this is for dependent situations. And that's what we just did along the arms of the tree diagram. Okay, this was our conditional probability. Okay, all right, so that's our dependent. So if A and B are independent, then we know the probability of event B happening given A is already happened is no different than the probability of B all by itself, because remember, the percentages will be the same if they're independent. Okay, so if that is true, the probability of A and B is just the probability of A times the probability of B. So if we were to flip a coin a bunch of times, so if I want to know the probability of 3 heads, it'd be the probability of the first one being a head times the probability of the second one being a head times the probability of the third one being a head. And that will give me the probability of 3 heads in a row. Because coin flips are not dependent, they're independent events. However, if I'm dealing cards, like I was doing earlier, I have 5 cards. Once I deal one of the cards, now I only have 4 left. Once you know there's a king that came out, it changes what you know what's left in my hand. That makes it dependent, and that's where this situation's coming in. But mathematically, it looks like you're doing the same thing. You're still multiplying. It's just one of the numbers is conditional. Now, if I had dealt that king out and then picked it back in and shuffled it back in, well, then I would have still had 5 cards, so the probabilities didn't change. Then it would have been independent. So it just depends on whether or not you have replacement when you're playing with your cards. All right, so let's see what else we've got. We got our tree diagrams here. So, like I said before, these can get as big as we want to make them. I'm going to make a smaller one because you get the idea after just a couple rounds here. So we have event A, and we're going to call this event not A, or A complement. So we want to have the probability of A. This will be the probability of A complement. Okay, those should add to 1 because it's 100% of the choices, because we've we said there's two different things. So if a certain percentage go here, the rest of them have to go there. Okay, from here, we're going to reiterate, we're going to make this happen again, like deal another card or flip another coin, and you have different outcomes that can come off of this. We're going to call them B and C. We can keep going, but we're going to keep it a little more limited. So remember what I said before, that when you go along the arm, that's a multiplying situation, because we're saying A and B. So this is and. So when I have this is going to leave me and give me the probability of A and B. When I follow these branches, it's going to give me the probability of A and C. Then I ran out of branches up there, so I'm starting back over. This branch will lead to the probability of A complement and B. And then finally the last branch will give me the probability of A complement and C. Okay. And so we're multiplying across the arms, but if I'm trying to ask about this probability or how many ways can you win this, because I can win it this way or that way, the word or keeps being in there. So that means you add between the probabilities when you're going between branches. And when you add all of these probabilities up, they're going to equal 1 to be a valid probability model. All right, one last thing. There's something called the probability of at least 1. So the probability of at least 1 equals 1 minus the probability of none. So let me show you what I mean by that. If we were going to throw a baseball at a stack of cans 5 times, how many ways could my results end up? How many times could I end up hitting that stack of cans? Well, I could be really terrible at this game and I could hit that stack of can 0 times. I could hit the stack of can 1 time, 2 times, 3 times, 4 times, or I could hit and be awesome and hit it all 5 times. So these are all the possible outcomes that I could get. If I want to know the probability of hitting at least 1 time, well, at least means from here and bigger. So I want to know the probability of all of these added together. So you could add all of those together, or this little guy, who's the only one left behind. If I take 1 minus this, it tells me what all of those are added together. Because sometimes you don't know the individual probabilities, you just know enough to be able to do 1 minus the probability of none. Right? So what I want you to do is I want you to pause your video. I want you to give this a good try all on your own and see how you did. Come back when you're done. All right, so let's see how you did. This one, the wording was a little complicated. So it said 30 states went Republican candidate and 20 states went to the Democrat candidate. So I had Republican and Democrat. 30 of the 50 went to the Republican and 20 out of the 50 went to the Democrat. Okay. Then they gave us some more scenarios to split off from there. And so when I wanted to know about continental U.S. and not continental U.S., I was multiplying across my branches. So, and I wrote them as fractions out here, but I also have them as decimals: 0.58, 0.02, 0.38, and 0.02. Okay, so hopefully that went well, and you can always double check yourself by making sure they add up to 1. If they don't, go back and check your work. All right, for part B, we wanted to find the probability that a randomly selected state is in the continental United States and went Republican. Okay, so we want continental United States and Republican. Well, that's our first branch up here. There's Republican and continental United States. That was 29 out of 50. So 0.58, which is 58%. Okay. Usually we're going to leave them in the decimals for these. Now, if we select 4 states at random with replacement, meaning we could reselect them again, and the reason that's important is their probabilities don't change if there's a replacement. It's the same each time. What is the probability that at least one of the states in the continental U.S. went Republican? Okay, so I'm going to use this 1 minus the probability of at least one is the probability of 1 minus the probability of none. Okay, so if the probability of Republican and continental United States is 0.58, 1 minus 0.58 is 0.42. So that's the probability of not Republican, not continental United States. But I did this 4 times, so I want a state and a state and a state and a state 4 times. So I'm applying this exponent to this. It's not multiplying by 4, it's itself times itself 4 times. Okay, so 1 minus 0.42, and only the 0.42 is raised to the 4th, so I would get a probability of 0.9689. All right, and our last question. Given that a randomly selected state is not in the continental United States, what is the probability that it went Republican? So I wrote my symbology here. What's the probability of Republican given not continental United States? So not continental United States happens in 2 different places. We have this 1 out of 50 right here, or we have this 1 out of 50 right here. And so that's where these are being added together, because that's that or situation, because I could do it this way or that way. And then what's the probability of Republican given that this has happened? Well, that only happened in 1 place, and that's right here, 1 out of 50. So that's where this 1 out of 50 came from. When I do my math down, there's a 50% chance that if they're not from the continental United States, they went Republican. Hopefully that was helpful. Let me know if you have any questions, and I'll see you in class.